we just recall something. See, the one we want to study is like representation of GQP. We have V here, right? So the general picture, I write it again. And then here, so by phi gamma module theory, so you get this dV, and so it's phi gamma module over E. And the one we want is this. We want the correspondence, a conjecturally correspondence is 2 pi is representation of GL2 QP, which we write is just G. So this is a general picture. As I said yesterday, we need to find some bijection here. So this is a periodic local Lorentz. So the what we want here is we want from pi. So this is pi. We get something d of pi, and from this d we go back to get something pi of d. So this is the general picture. So the first thing today we want to talk about is, I think it's section 4.5, is about representations of G. So we want from this pi, we get a d of pi. So we recall this general notation. So Z is the center of G. K is just GL2 ZP. So it's a maximal compact subgroup of G. So we also have Kn is just the kernel of GL2 ZP. Goes to GL2 at the module P and Z. So we have this kernel. We also have this W is 0, 1, 1, 0. Okay. At this moment, maybe we also have this B is Borel. So this Borel subgroup AB 0D, and P is parabolic or parabolic, whatever. Okay. So now pi is just a representation of G. Let's see. Now, what is pi? So we will have those something called admissible, irreducible, all this kind of thing, right? So a representation of G pi. A representation we know is so it's just say we have is an OL module. So here, so if it's OL representation, okay, of G, it's an OL module plus G action. Certainly the G action should be continuous. And say G is pi at this, a central character. Delta pi so you have the central character is if G in Z acts through delta pi. It's just a multiplication. So that means if you have element like GV, it's just delta GV. Okay, delta pi GV. So this delta pi, we call this is the central character of pi. And also delta pi is locally constant, or Lis. So this is a French word, Lis, if the stabilizer of V in pi is compact, is open. The third one means pi is admissible if pi kn is the one fixed by kn is of finite type for all n. So this we have all this definition. Now we let pi is contained in this tau G. So this means locally constant, admissible, with the central character, and we also need, because it's torsion, so it's of finite length. So we let pi is all these kind of representations. Now we let W pi is all this W contained in pi is a module, is OL module or finite length. So we have this such that W is stable by pk and generates pi is OLG module. So we let this curly W pi and this kind of thing. So the first thing you want to know if this exists. So one thing is this is not empty. Okay, so this is not empty. Now because of this is not empty, so we have this kind of exact sequence. We have IW is just the induced module from Kz to G, because this W is a Kz module, right? It's invariant by K, certainly it's also invariant by Z, because Z is a central character, X through central character. So because of this condition, this W generates pi. So then pi is a quotient of this. Okay, so we write this as a R pi W. So we have the exact sequence. Now this exact sequence, so we call this is a presentation of pi. So this is a, so IW over R pi W a presentation of pi. Now, a presentation is called standard. If this R pi W, then this R pi W is generated by all the edges. So this is some technical condition. So all the relations supported by edges of the tree of P GL to QP. Okay. So what is this tree? This tree is just like this. The tree, you know, we have vertices and we have edges. So what is the vertices? Vertices is just all this lattice in QP E1 plus QP E2. But you need module the scalar. So up to homosity. Okay. So the edges, so two vertices are connected. Is just say the distance is 1. So it's just S prime. That means if you have one lattice here, you have another lattice here, but you need to choose the representative, and then you see the quotient is a module of is a dimension 1, is of dimension 1, then that means the distance 1. But anyway, there's some condition in the tree, in the serial tree. Okay, so this tree, so the vertices, the vertices of the tree is what? The number of points, vertices is just G over KZ. It's just connected to this. Okay, so G is the G we have here, K is the maximum compact, Z is the center. So this relation is a presentation is standard if this is supported by this. And then the theorem, the first theorem of Taylor is saying every pi admits a standard presentation. It's from this kind of standard presentation we get from pi, we get pi d. Okay. So this is the idea. You first need to get a standard presentation. And this result is proved by many people. So in this paper, Kometz gave a proof. And also there's some proof by Bohoy and Pascunas. In the traditional case, it just means L is not P case when the characteristic is 0 or not P case. That was a result of Schneider and which one? Schneider and Winnihaus. There are many people prove this. Okay, and also this is not true. So remark. Not true. So this is by Pohoyer. If you want to extend the result, so if you want to change QP to other L, it's not true. if we replace QP by some, say, some F. Okay. So that's one of the difficulty. So here, Konosu data is proof of the local periodic Lagrange in the over GL2QP, right? So certainly you want to extend to other local fields, but this is one of the local difficulty of other fields because of this is not true. Okay, so there are lots of things you need to worry about, and much research is doing right now on this subject. Okay.
One question. So there in the exact sequence, you wrote the induction of the capital W.
Yeah.
So what, is it the same as here W? Or?
W. So W is any W inside here. So for any W. Because of the condition, the definition, so this pi is a quotient of this, because W generates pi as a G module. You need to use this condition. Okay?
So the maybe that's the that
Which one?
induction to pi is just the exact sequence. Yeah.
What is this?
From there to pi is just the what is the map from
Well, it's just
W to pi?
yeah.
So what is the map?
Well, I think this is a very natural map. Yeah. Yeah, you can say, well, you can say like GW, you go through GW. Something like this. But this one you need to say G is a function extending this, and then you goes to this. Yeah. This is a very natural map. It's just because of this. So if you have this kind of condition, you always have it. Okay. So what I mean here is this pi is only so for this pi over GL to QP of this G. So this is not true if GL to F. Okay. And this is proved by Buhoy. Give some counterexample. Buhoy and Pascunas. And this is one of the difficulty. So how to extend this result to other fields. Now we need from pi to pi d. So we still suppose W is contained in and induce a standard, inducing a standard presentation. Then we can define many subjects. We could define one subject called IZP pi W. So what is this? It's a submodule of pi. So it's generated by all the relations. So it's P of NA01W. And for A is contained in the P. Okay. So it's generated by all this this A. So and then you have the dual of pi. The dual of pi is this Pontryagin dual is just say is pi is OL is LOL. Okay, so this is just the Pontryagin dual of pi. So then we have this one. So this one is D natural W of pi. So this is the dual of IZP pi. W. Okay, so this is a submodule of pi. So that means because those are dual, so that just means this is a quotient. So is a quotient of pi check. Okay, the punctuation dual. So we note this ZPW. So this is a natural map. So this is a natural map, the restriction. Now the thing is, we can have another one we call D plus W pi. Here we have D natural, so we have D plus W pi. So what we get is just say all this mu is contained in here, such that this mu Pn A01 W is 0. For any A is not contained in the P. Okay. Yeah. So now this is a submodule of this, so we get a natural map from this D goes to okay. So the good thing is this gives an injection. So actually you give an injection of this because of the composite. You can check this is actually an injection. Now this injection will have some good properties. So this will have the PZP action. So P is a parabolic subgroup. So it's a PZP action. So if we let T, it's just a 1, 1, 0, 1, minus 1, because this is T plus 1. So we always have this. If we let the gamma A, it's just say it's A, 0, 0, 1. This is also natural. And then both of these is so they have this action, they have this action. They are phi gamma modules. Over OLT instead of PZP module, we get phi gamma module. Now this phi gamma module has something good. So if we tensor this by OE, then we have the isomorphism. Then DW tensor O is OLT module. These are isomorphic to and then this is OELT phi gamma module. Over this, right? Because this is that one. This. So now we just let this is D pi. This is just D pi. Because from this pi, we really get a phi gamma module. This is easier because you have this PZP action, you already T and gamma A, and then you get this D pi action. So this is D pi, and we also have this this map pi dual, we can first goes to yeah, we can just goes to d pi by the x goes to 1 tensor x. Okay, so we have this map beta ZP. The thing is, this is independent of W. So you can choose another W, you still get this one. And also, so beta ZP is independent. And also d pi is also independent. Of W. So because of this, we don't have pi in here. We don't have W here. We have W here, but if you tensor over this one over OE, you get something. It's a phi gamma module. So that's the first step from pi to d pi. So the theorem, certainly the first theorem is, say, if pi is tau v, then d pi is contained in phi gamma eta torsion GQP. So this is the first one. The second one, the functor pi is contravariant and exact. Okay, so this is the theorem for this section. So one thing you need to know, so why this is contravariant? Because you see this d pi actually is constructed from the dual of d. So if you really want to find a covariant one, so you need to take the d pi dual, and then you get a covariant one, and then it's also exact. So this is one thing. And the other thing, the third part of the theorem, you can construct this. This looks easy. You can just construct it. So the hard part of the construction is prove this d pi is actually of finite length. So this is not easy. This is hard. And to prove it, you need to use phi gamma modules. Okay. And to prove the exactness, okay, so to prove this exactness, so that's you can first reduce to this pi is irreducible, and then you use a classification of pi. This was done by Bohoy and Bartel and Wine. So this kind of, for the irreducible representations of over G, you actually have a classification, the irreducible object or the irreducible object already classified. So this is also the problem now, like in this one. See, for general F, you don't have this kind of classifications. For QP, it is done by Bohoy and others. Okay, so this is the first step. It goes from pi, you get d pi.
The exact sequence induction is in the first exact sequence there.
Yes.
The map still just quite mysterious, because the induction is kind of maps functions which G to W vanishing on KG.
Yes.
There might be somehow something independent representative G modulo KG.
Okay, let me write down this map.
Independent of G.
Yeah, let me write down this one for you. Let me find it. So for example, I just erase this one. So what is this? This is just all the functions, right? Or you can say from G to W, and also is with support in finite modulo Kz, right? Such that maybe phi Kh is K times phi H for K is in Kz, H is in G, or something like this, and it's just some technical condition, right? So now you just define this phi. What do you get? You just send phi to this. Okay, so this is a finite sum because this is finite support here. Okay, so it's just this. Or you can also define some other map, like if you can, like this map GV of H. I just define is HGV if HG is contained in Kz. If 0, otherwise. And then this you can use this one. Is GV, it goes to G of V. And then you can also get the result. So here, V is in W, G is in G. Okay, so you will use this map, and then this just send to this. You can also get it. Okay, so that's the map. So this is the first thing we actually get from pi to d pi. Now we can study a little bit more about how, if we get d pi, how can we recover pi if we know, and then to get some clue from d to pi d. So now our next sorry, we haven't finished this yet. So this is only for this one, for pi is in here. What about in other? So what about if pi in, it's not torsion, it's just a finite length, but this is easy. You just let d pi, it's just the project limit of d pi over Pn pi. And then all these are torsion, so you can do it. So what about if pi in L, then you just d pi is some d pi 0, and then you tensor O L and L, and pi 0 is a lattice in pi fixed by G, stable by G. Just means pi 0 is contained in here, so you just take this and then you can get it. Now what is V of pi? So V of pi is just we can take the tape dual of V d pi. Now you can see, because d pi, pi to d pi is contravariant, but you already take the dual. So then pi goes to v pi is exact and covariant. So that's the real construction from pi to v pi, and also from pi to d pi. So you get this, okay. And you have others. So this is this thing. Now we want to say is from the second section we have this is about the contract gradient. Of pi. So if we have a pi here, how can we construct? So the problem is, how can we reconstruct pi from d pi? Because we want from d, we want to get a proof b. But first, let's see in this kind of special case, how can we reconstruct pi from d of pi? And this, we just let d is d pi. Delta is delta pi, the central character, and to the -1. So we just write on this. Now we suppose pi doesn't have a finite quotient. Okay. Now, yes?
So your v pi is take the dual of
yeah, of this v d pi.
v d pi or just the d pi?
V d pi.
V d pi.
Yeah, d is phi gamma model, is not a representation yet. So we need to take v to be a representation, right? So this v means GQP representation. Pi means G representation. D is phi gamma module. So if we just take what is the theta d of pi? I don't know. So you need to take the theta d of v d pi. Okay. So the proposition here is we need to use this beta zp. So first we can define something like beta qp. So this we can say if we can have a map from beta qp from this one, the dual, the Pontryagin dual, we can get to this d qp. What do we have? We have is, so this mu we goes to this beta zp. And then we have Pn001 and mu. Then n is contained in n. We have this map is a B equivalent morphism. And kernel is, for the kernel, is some pi u and image contains the, so it's contained in here. Is QP and includes so you will have this beta QP. So it's between these two, and it's contain and the difference and with equality. So this one with equality. If pi contains no finite representations, no finite sub-representations. Okay, so just means this will be equal to the second one if pi contains no finite representation. So this is a beta QP. Now define beta QP, and we can also define beta P1. So what is beta P1? Say we have is this map, is this to D cos D, and then we have mu we have this. The theorem is this. Say, so beta P1 of this, the image of this, is still contained in here, and is G equivalent. So here is B equivalent, but this is G equivalent. And the second one, if you take a restriction of QP of this beta P1, you just get this beta QP. You take restriction. This restriction we studied last time. And the third one is, this one is injective. And this image, so it's contained in here. In all this D contained in D, such that QPZ is in D sharp. Okay, so oh no, this is QP. Such that it's this. So we just let this is just maybe it's just a D. Okay, so the same thing we define D. So we have this D. So under the same definition as above, then this one is contained, is stable by G. So it's a G module and contains something, the orthogonal image of pi SL2QP as a submodule of finite index. So this is looks technical, but then the thing is, if we let pi check, if we let this, it's just this one, and divide this one. Divide by this map, then what we have is theorem is say this is almost the so the first one is contained in here with no finite quotient. And the second one is this one, the conjugate gradient. So this should be above. Okay, it's just pi. So the conjugate gradient representation, yeah, is just pi, or you can say it's naturally isomorphic to pi. So that means you see if we defined if we want from D we want recover pi, we need something this divided by this, and then this one from the theorem saying this one is something close to here. So it's something close to here or close to here. So it's very close to this one. Did I write more? Yeah. Yeah, so it's very close to this one. So the clue for the next step is we want from D goes to D of pi, or goes to pi of D. So we need something, this one divided by something close to this, and then a candidate is just this. And then so we will find it will be the case. So that's from the second one. So let's move to the periodic, so-called periodic local Lagrange correspondence. Or maybe we have a rest. Any questions?